So where I left off, let's see, here we go. Hello everyone and welcome to Handmade Heroes, show where we code a complete game live on stream. We are streaming over YouTube today because Twitch totally rolled over and died on us and is refusing to let us stream anything at all. So that's just where we're at. Hopefully everyone can hear me okay and see me okay. If you can't, I am recording this locally, so hopefully we will be able to post it online and you can watch it after the fact. Where I left off yesterday was I just cranked the number of things in the scene up to the full size that will probably be in a rendered scene in the actual game during gameplay, so that we could see the slowest the lighting would get. Right now the lighting is totally unoptimized, and so the idea now is just to start working on optimizing the lighting to get it to a point where we can run it at 60 frames a second. Now, I don't actually think this is going to be that hard because we found that for a simplified room, one that we were not actually doing the size of a real level where there was lots of stuff in it in the simulation region. In that case, we actually were running just fine with the completely unoptimized lighting that was super crappy in terms of how it does performance. And so that's just a good example of how fast computers are these days. When you have relatively simple level geometry, you can just have them light the whole thing. So we've gotten it now to a point where it's relatively slow, and so our goal is now to start thinking about how we're going to get this running faster. And so really we're just looking at streamlining this stuff and starting to think about how it's going to be spatially partitioned, that sort of thing. So let me go ahead and show you what I'm talking about for those of you who maybe didn't see yesterday's stream or who have very short memories and can't remember what happened on yesterday's stream. I'm going to go ahead and run this here. And what you can see is we get a very, very slow frame rate here because the level is nice and big. You can see up here, you know, it's like 1.2 seconds per frame, right? That's what happens when we get a whole level size. And so that's just an example of where we are starting from. Now, our goal, of course, is to make it run nice and smoothly there. And again, I don't think that's going to be too much of a struggle, although it will take, you know, a few steps to get there. If I show, let's see here, if I make it so that it doesn't quite generate as much stuff as that, for example, if we just generate a single scene, a single room, whatever you want to call it, then we can actually have fairly playable rates, right? So, you know, even the completely unoptimized version, it doesn't really run in real time. It runs in interactive time, though. And the lighting works with shadowing and everything else and all that good stuff. So we're in relatively good shape. I don't think we're going to have to struggle too much, but we do need to do a bunch of work to get us to the point where we'll be running at 60 frames a second with real lighting. So let's talk about what the source of the slowness is in this algorithm, because right now whenever you look at an optimization problem, right, there's different sort of slices of the optimization that you're thinking about. And in the case that we're talking about right now, we're really talking about algorithmic optimization. So what I mean by that is obviously there's, you know, very meticulous optimization of like what the actual CPU and GPU are doing, and talking about the exact performance characteristics of that and so on. We're not really at that point yet. We haven't even moved lighting to the GPU. We're actually doing lighting entirely on the CPU right now. And we're not even doing it with SIMD or any of that stuff. So we're not talking about optimizing the lighting from a processor standpoint yet, because it's a little bit premature. What we're talking about right now is just let's architect the lighting algorithm so that it's running in a reasonable way that we think will give us reasonable performance, right? Because there's only so much you can do to speed up the computation of the lighting brute force, which is how we're doing it now. What we'd rather do is use some more subtlety in the way that we compute the lighting so that we don't have to do as much work just in the abstract sense, right? The actual number of work items we have to actually do to perform the lighting, we're trying to reduce that down rather than talking about speeding up an individual piece of work, right? And those are sort of the two sort of big parts of optimization. So we're not really going to be timing stuff right now or getting into instruction because that sort of stuff. We're just at a very broad phase where we need to just reduce the total amount of work we're even considering because that's already just out in a ridiculous place. Okay. So let me show you what I mean by that. So if we go into the render group here, what you can see if we look at the compute light propagation function, and I think now we did solve this problem. I guess I should say that the index assignment is not quite done yet, so I'm going to still put one here that says, you know, we want to make sure that we do index reassignment properly. Because right now, if you started to move around the scene, we wouldn't necessarily, we don't have a way of like freeing light indices when they're not used. So we want to make sure that we do that eventually. It's not important to do right now because we're not moving around. So we don't have to really, inside the light algorithm itself, it doesn't care because the lighting indices have already been assigned. But once we sort of finish the lighting and say that's done, we do in the renderer need to have a little thing that can allocate and deallocate light blocks, basically, so that they are that they correspond properly. And this isn't about memory allocation; it's just about correspondence allocation. Again, because rather than doing spatial correspondence, we're just doing ID-based correspondence to keep it really smooth and clear, right? So this is presumably where we're spending all the time. And why do I say presumably? Because I haven't actually measured it yet. But what I can pretty much tell you is this is our problem. The reason that I know this is our problem is because it is way too loopy, right? Loopiness equals slowness. Basically what happens is here we have a number of light propagation iterations. So there's one, you know, if you imagine the amount of work that has to be done, I'm going to go ahead and switch over to Milton here really quickly just so I can draw this out for you. Here's day 420. So let's talk about the lighting work here. So if you look at what we're actually talking about, we have a number of iterations. So we have to do the number of iterations. And then it's going to do everything inside. Why am I not? There we go. So we have however many iterations we're doing, right? Then we're going to look at every emitter, right? So times the number of emitters. Then we're going to look at the number of rays, which is the ray count here. And then for each one of those, we're going to look at the raycast function itself, right? Here's the raycast. And that's going to go over all the surfaces. And we end up with this really big, nasty equation for the amount of work that we're going to do, right? We know that this thing is not particularly high, right? I mean, it could be as low as something like 4, right? It's not a particularly high number. So that's not the end of the world necessarily, but you know, you get the idea. So we have a certain number of iterations. We have a number of emitters. This is going to be huge, right? This is going to be on the order of like 32,000 or something like this, right? This is a huge number potentially. You know, we can get that down certainly to a lower number, but this is going to be huge. So, you know, maybe this gets down to something like 16K or something like that. But all of, remember, emitter is just a term here talking about surfaces that are reflecting light off of them. So really, it's every surface in the game is in this emitter category here, right? Then we have some number of rays, right? And the number of rays goes potentially down with each iteration. But, you know, this number here is going to be something in the range of like, you know, between 4 and 64. So it's, again, a pretty high number. And then the number of surfaces is basically the same as this, more or less. There's less surfaces than emitters because surfaces are a big sort of occluders, whereas emitters are individual points that might be, you know, receiving and sending light. And so then in surfaces, let's say, you know, there's a significantly less than this, but there's still a large number, like 8,000 or something, right? So when you look at how many of these things we have, you can see why this is something that can't be run in real time the way that it is written at the moment, right? Oops, I remember people gave me this little speed crunch thing here. So yeah, I'm not really very familiar with speed crunch, but it seems like a reasonable thing to use. So if we look at what happens here, let's say we do 4 times 32 K, then times, I don't know, the average of that, maybe let's say is somewhere around 24, depending on how, I don't remember exactly how we break it down, but it's something like that, times 8,000. And you can see that it's just this ridiculously massive number here, right? And remember, the number of cycles per second we're going to get on something like a CPU is, in the ballpark of this, right? Right, something like 3 gigahertz is what we're expecting to get in terms of cycles. And so when you compare these two things together, it's just a really unflattering comparison, not particularly good at all. So you can see why you start spiking up to really high numbers, because you need just a ton of computation time for something that does this much work, even if the work is very simple. And mind you, the work is very simple. These are just ray checks. It's not doing a lot of math, but it's enough, right? So you can just see that these numbers have to be pared down substantially. So if you were to imagine how you might pare these numbers down substantially, right? You got a number of ways that you could start to look at reducing these. First of all, this is a really easy number to start reducing right here. And so in some sense is this one. And so let's talk about that, because the ray count and the iteration count themselves are very minor, right? We're talking about worst case, it's something like this. I mean, it's actually, I think it's 64 like plus 32 plus 16 plus 8. It's something like this, right? It's a very low number. So the number of ray casts we're actually doing just in terms of the iteration and rays is extremely low. It's just because there's so many things to raycast from and so many things to raycast to. Doing 120 rays, millions of times is, 120 millions of rays. You get the idea. So what we're looking at here is these are the big numbers. These are the really big numbers that are blowing out our system. So what we're really looking at here is, forget these, because these are not that important and can be addressed in a number of different ways. These are really not that important. It's these that are important. So what we're talking about here is reducing the emitter times surface, ON squared, part of this problem, right? Because these are both proportional to n. They're proportional to the number of things. That looks like an H. I apologize for that. These are both proportional to the number of things in the game, right? The number of things that are bouncing light around and the number of things that are stopping light from bouncing around are both proportional to the number of things in the game. So the number of things that we have in the game squared is going to be this, central problem. So as we crank that number up, right, that is where we get into hot water. So the question is, how do we do something that takes this central product and reduces it to something that's more manageable, right? How do we make it so that we can still do something? Because we know the lighting has to do this. We know the lighting has to be about all the emitters emitting to all the surfaces. So how do we do something smart here? And so the answer is we're probably going to end up with something that's multi-resolution, right? So what we can probably say is, all right, look, let's say we have a fairly detailed thing in the scene where we've got, sort of all of these cubes right around, and they're all kind of bouncing light around in each other, and they're stopping light from coming in from the outside and whatever. Obviously, we need to do a full n squared thing on these 5 emitters, occluders, whatever they are. Well, I mean, everything is kind of both in the game, right? So we need to do something like that. So, we might have a 5 times 5 kind of a situation here that's 25 things, right? But that's a totally reasonable number of things to do. And then over here, we may have a similar thing set up, right? That's bouncing light all around it, right? And maybe there's 6 of these, right? So it's a 6 times 6 situation, right? Again, totally reasonable. The problem comes when these interact with each other now, right? If we aggregate everything up, then we start saying, well, now it's, 11 times 11 if these all have to go into each other. And now we start to get into much higher numbers, right? This is a much higher number than just doing these two things separately, right? 25 plus 36 is much lower than 121, right? And this gets worse and worse as you go. This is the ON versus ON squared problem. If we just look at little local clusters and add them together, that's going to scale as a nice line. If we always put them so that they all have to compute crosswise, that's where we get this sort of nasty spiral off into infinity kind of ON squared thing, right? So this is our ON squared curve, this is our ON line, and we want to try and stay on this line as much as possible. This is where 60 frames per second lives. This is where, you know, I don't know. This is where a PUBG server lives, right? It's out on this ridiculous line where you can't even, you know, you rubber band all over the place. So this is what we want to be. We want to be on the 60 frames per second line. In order to do that, we have to break this n squared problem. And so when I say multi-resolution, what I'm saying is let's look for ways that we can cleave these things apart and say that things that are next to each other we will solve n squared because that's how light transfer works, but can we basically break things into clusters which will then just transmit light as clusters to each other? And if you remember when I started out the lighting thing, I was talking about doing lighting in this way. We just never actually got to a point where that multi-resolution thing, I wasn't sure how it's going to work. So now is the part where that finally comes in. Now we can actually implement something multi-resolution because we have an algorithm that's actually working with full n squared, and now we just need to figure out a way to break it into something that's based on less, how should I put this? That's based on more of an ON curve of breaking things down into smaller sections. Now, there's, again, two ways you can sort of look at this problem. You can look at this problem as ON versus some small number, right? So we can look at it as ON versus some very small number, right? Or we can look at this as, you know, small number versus small number. And I want to talk about the difference between these two things because they're two different types of algorithms. So this is the standard raycasting approach for like offline rendering. We still loop over everything that is going to be doing, say, transmission or something. So we still loop over 32,000 things for transmission or reception, whichever one we want to do. But then we employ some kind of a spatial partition so that we only consider a subset of the n when we actually go to do like intersection or something like that, right? So for example, let's say we have a KD tree. We've talked about these before, or an oct tree, or a quad tree, or a BSP tree, right? Let's say we have any kind of spatial partition. So one way of looking at this is saying, well, let's loop over everything we were going to do before. So for example, up here when we wrote this giant equation, let's say that all of this is going to be exactly the same as it was. And then the only thing we're going to do is employ a spatial partition here, one of those tree types here, so that surfaces instead of being ON is like O log n or something, right? So this is our small number. So it's saying, take all of this, leave them as large numbers, knock one down to a small number. But this guy is still ON, right? That's one way to do it. That way will be slower, but potentially more accurate, maybe. It's still operating on everything, right? That way will be more accurate, but slower than something that is not actually accelerating the exact equation, right? Oh, it looks like Steam is still running on my machine. How do I exit? There we go. Sorry about that. Little Steam toasts. They're everywhere. So basically what I'm trying to say here is, if you take a look at how that was working, we're taking one part of the giant multiplication expression and we're simplifying that one down to be a small number, but everything else is working exactly the way it was. So we're really just accelerating one search part, one part that was saying, what did I intersect? We're accelerating just that one part, right? But another way of looking at it is, again, sort of the multi-resolution approach is not that. The multi-resolution approach says, let's simplify things down so that rather than ever working on the whole problem exactly as it was, we're just going to work on clusters that sort of smush down into approximations for areas. And so that was sort of what I was interested in exploring now in terms of how we accelerate things. And what that means is exactly what I was drawing before. When we have sort of that example that I was saying, oh, you've got these people that are transmitting light, right? Well, the way that the tree-based sort of accelerate just one half of the problem works is when we go to transmit light, say, from here to here, what we're doing is we're saying, well, we binary space partitioned this or something in some way that cleaves up the space so that really we just do, instead of having to check against all 6 of, well, not just all 6, but all 11 of the things here, we're only going to do like a couple plain tests, so like 3 tests, and then we know that we only really have to check this guy or something, right? So again, we're doing exactly all the same work as we were doing before, but we're just knocking down the number of things we consider when we go to do our expensive test, right? The multi-resolution approach is different. It knocks everything down to small numbers. The way that works is says, let's identify clusters that will transmit light amongst themselves and have some idea of how the light transmits out from them. And then this whole segment gets reduced to just its cluster, right? So now this thing is just a single, it's one emitter, occluder for all 5. Same with this one, so that by the time we do transfer between these 2 things, we're talking about a 1-to-1 transfer, right? And this is, I talked about this as a multi-grid, right, approach to lighting. Go. And what that means is it's saying, okay, let's just say there's a very, we have a very granular 32,000 things or whatever at the bottom. We're simply not going to do light transmission between 32,000 things. We don't even want to consider that as an option. Instead, what we're going to do is we're going to bounce light around clusters of these things that then collapse in on themselves into sort of smaller and smaller groups. Those groups then transfer light between each other and propagate back down to the lower levels, right? So I don't know. These are 2 ways of approaching the problem. One benefit of the one that is not multi-resolution, that's basically just saying, hey, let's go ahead and just use acceleration for the query, is you don't have to worry about how those cluster boundaries affect things. The strictly multi-resolution approach, which is an up iteration and then down, like n up iterations and n down iterations, is that it's perfectly log n all the time. It always is looking at subdividing thing, it's not subdividing, how do I say it? Like sub-collapsing, right? It's reducing the numbers up, does some things and then goes back down. The problem with it, of course, is that you have to figure out what you do at these cluster boundaries to not see seams or things like this. And so one potential way that we could mix these 2 approaches together is to, sort of take a page from the thing that we were experimenting with early on as well, where we actually do still loop over every receptor surface, but when we look at where it's getting its light from, we do that in a multi-resolution fashion. So we just look at things that are far, we sort of have some entirely grouped version, some tree that talks about grouped occluders emitters, and we just go through that sort of grouped version, and we subdivide it down to as detailed as we need to in terms of things that should be considered. So the way to think about that is that we have some multi-resolution version of this thing where, okay, let's say that here's all of the things we have in the scene. And we start the lighting algorithm by just collapsing everything up into a tree. So these things form a tree where there's a root node, right, that encompasses everything in here. It's split into some number of child nodes, right? Those are split into some number of child nodes, blah, 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 right? And then eventually you get down and the leaves are individual ones of these, right? So we just have an entire tree. When we go to compute a lighting transfer for any given one of these, what we do is we use the leaf nodes for the things that are close to it. So these things, let's say here, are all involved in direct computations. But then anything that's further away that doesn't need to be split, say this cluster here, this cluster here, this cluster here, maybe that's cluster, right? Just transmit light as a group. You know, they transmit and block light as a group. And, you know, I don't know. Is it the right way to do it? I'm not sure. It's just a thought, right? And so the way that I'm thinking about that is to just say, okay, for any given lighting computation, we just have a tree walk that goes downward. That's something we can implement in a shader, assuming the tree has been built ahead of time. Building the tree in a shader might not work, but that's okay. We could build the tree on the CPU. So basically the CPU builds the tree and sends it down. A compute shader could build the tree just fine, but I don't know that we want to go into that territory because sometimes you're, you know, better off keeping things simple enough that you don't require compute shaders. So anyway, that's the sort of thing that I'm thinking about, is just could we maybe multi-res it on just one side, not on the other side. So we're still not doing the thing where we're doing, you know, technically ON squared, but we're breaking one half of the ON squared by using a spatial partition. Instead, we're doing ON versus some sort of multi-resolution thing where we're not even doing spatial partitioning to figure out what we hit in a faster fashion. We're literally testing against things that are multi-resolution as you go further out. So that's my sort of rough feeling on that. And, you know, in order to do this, I think because our world is kind of cube-like, I feel like one thing we could do is just do all of this on cubes. So we could say that every lighting element is really just a cube, and, you know, we just sort of coalesce these cubes together, and off we go. So we would have sort of the way this would look is we'd have a giant, like, mama cube, you know, which would be sort of the cube that contains all cubes. Then inside there we have, you know, some smaller cubes, and inside those cubes we have smaller cubes yet, until eventually we have the level geometry, right? And the way that we would build this is probably doing some kind of thing where we take closest, you know, at the beginning we sort of take a spatial partition and dump things in and find the closest cubes. We collapse those cubes together, up and up and up and up, and we maybe group, you know, 4 cubes at a time or something like this, I don't know. So we can do something like that where we just kind of group these things together based on their proximity. And hey, our world storage already stores things based on proximity, so in theory, if we played our cards right, we could even keep that flowing through the whole pipeline and not have to do a lot of work to create the sort of higher order work there in the first place. That might be good as well. So I feel like we're, you know, that's based on the fact that our world is supposed to be kind of cubey anyway. It seems like that's the case. Now, when I say cube, I don't really mean cube. I really mean right rectangular prism. Obviously, like, it's something that has a width, a height, and a depth. These are not all the same. It's not width cubed, right? So it's not really a cube. It's actually a right rectangular prism, but you know what I mean. So that is, and I more specifically mean an axis-aligned right rectangular prism, often called an axis-aligned bounding box, or AABB. So I think, you know, that's a relatively reasonable way we could start to approach things. And again, it's hard to know ahead of time whether it's intelligent or not. Sometimes you have to just explore. But that's, I think, what I would like to go down. And the steps to this would be basically like cubify the lighting. So basically right now we're actually talking about surfaces as being individual plates. I think maybe we switch to cubes because that way we can just talk about a whole cube at a time. And we know that everything is always a cube. Or right rectangular prism, or AAB. Cubify the lighting, build the cube tree, and then, you know, update lighting with the tree. And so it's actually 3 fairly simple steps. I think, honestly, this is the only hard one, right? The rest is just busy work, but building a tree of spatially coherent lighting elements is actually something that is a little bit touchy, right? Like that's, yeah, you know. So, you know, this is something that we can do, and I think this bottom step here, you know, the update lighting with tree. I guess there is some subtlety there, right? Like, so if you think about what has to happen there, if we imagine that we're talking about the concept that this thing is an emitter, then it's kind of, it's going to be a little bit subtle to say, well, if I've got a bunch of cubes and I want to talk about an enclosing cube, knowing how much light hits, like exits here, right, is relatively difficult. I say relatively difficult because it's not that difficult. It's just relative to the rest of the stuff we're doing. But honestly, I think all it is just saying, all right, when we do light transport amongst the things in the set and have a bound around the set such that when you hit that bound, you add lighting to the boundary element, right? So that these boundary elements gain their lighting from things that would have exited the volume, right? We store those up, and so then we just have two light passes. We have the emission phase where things are transmitting light amongst themselves here, and any light, errant light that would go out hits the boundary element, hits the bound, and gets stored there. Then when we do light transfer between the larger elements, they just transfer light among those bounds, just like they were in here, and they've got a larger bound as well, right? Then when we come down to propagate the things that come in, we just have that inbound lighting. Now, what we could do as well is stagger that by one frame. So on every frame, we just do an up lighting pass. That's all we do. And during the up lighting pass, we are emitting from these surfaces as well, right? In-skew surfaces, right? In interior surfaces. And I think that's a reasonable approach, right? I mean, I can't see much peculiar about that, right? Whether it works and whether it's great or not, I don't know. Again, you know, when you're talking about sort of exploring novel routines, you kind of have to wing it a little bit and just go with some experiments. The whole lighting so far has been experiments, and it's gotten us to a pretty good place. And so now we're just talking about some experiments to figure out how we get the performance up to where we want it to be. And so I guess that's, yeah. I guess that all sounds plausible enough to me that I think I'd be ready to pull the trigger on that. I'm just kind of ruminating it in my head a little bit and trying to think if there's anything that I'm forgetting there in terms of things that are why you obviously shouldn't start down this path, but I'm not really coming up with much. So I will say one thing that is kind of difficult about it, that I think is a little bit tricky, is that in the case of our world, we're talking about there's like things like lots of little cubes that make up the ground or something, right? And so what's going to happen if you imagine you take a look at these systems as they are? When you imagine breaking these into chunks, you're going to get something where you've got one bounding cube like so, and one bounding cube like so, and these are tight, right? So you've got cubes that are like this next to each other talking about light transfer, and then you've got an additional version of that, right? In other words, all of these cubes are tight together. If they were broken up in this way, those two are also tight together, meaning their faces are coincident. I think that's going to make it relatively difficult to do the light transfer. If these were sort of cubes that were floating in space, you could be a lot sloppier with how this was working because you don't have abutting faces of your sort of multi-resolution groups. But here we do have abutting faces, and I think that that's going to make the lighting transfer more difficult because when you're talking about two faces that are right coincident with each other, figuring out how the light transfers between them is relatively difficult. You have to start being precise with how you are treating values in the system because simple raycasting is not going to work. If you talk about two surfaces that are directly on top of each other, right, one pointing this way, one pointing that way, figuring out that the light that leaves this surface is 100% going to go into this surface, basically, is a lot more difficult than just having surfaces that are separated from each other. And again, it's because the raycast itself now is numerically finicky because you're talking about coincident points that are exactly on planes, transmitting to those planes. You have no room for error anymore. And so one of the things that we might have to do is sort of special, treat these values specially. We did say that they're going to be axis aligned. That gives us an advantage. The advantage that it gives us is we know that things are going to line up exactly. They're not, if you're talking about two planes that look like this that are right on top of each other, they're not going to line up exactly. Once you reduce them to floating point, they could look a little bit more like this, where they're even though they're supposed to be exact, they're sort of tilted. With axis aligned stuff, we know that the value of x here will be exact on both, so we can actually check for equivalence. If we want to, when we're building these things, we could, in theory, make that work. You probably don't want to, but, I'm just saying we have some advantages that it's going to be a little bit more numerically feasible to work with because they are axis aligned than if they weren't axis aligned for when we do our transmission in that case. So, yeah, just trying to think that through. How problematic is that going to be? I'm thinking about in my head, I'm thinking about the case for the floor. So again, we kind of have these grounds that we want to look sort of cube-ish. And they kind of look like, if this is a floating piece, there's another piece next to it like this and so on. And I'm just thinking, so there's some unevenness there. And so you're going to get situations where you're looking at the side one of these larger cube transfer elements, and it's actually got the elements inside it kind of look like this, let's say, on the other side. So when you're asking about transmission between these two, I think we solve, again, that problem by just having points scattered on that surface each time we kind of go up. So you kind of know whether the transmission is happening more at the top or more at the bottom. So I think the, cubes with points scattered on them approach is actually relatively stable the whole way up, and hopefully will just kind of work. Again, we just have to make sure that we're really careful about allowing points that are right on the boundary to transmit properly. And I think that's all I have to say about it. How much time we got here? I don't even, because of that whole having to switch to YouTube because Twitch exploded disaster, I don't even know when we started this thing. Does Insobot on there tell us how far are we into the episode? We are 38 minutes into the mainstream. Okay. So we've got an hour and 20 minutes left, or something like that. At least an hour anyway. So we should be able to sort of take some first steps here. And I think the thing that we would want to do here probably is just, again, switch to cube-based lighting for this stuff. And that way we can start, right, because we've already got ourselves at a more granular thing that we're doing, which is actually just the plate-based lighting. we could stick with place-based lighting, but we would probably be somewhat wasteful there, because rather than doing things in terms of plates, we can just switch to doing things as AABBs. And one of the nice things about AABs is it's faster to check for intersection on them anyway, and that would allow us to get a speed increase on that part of the problem as well. One of the nice things about AABBs, again, is if you, and really not just AABBs, any bounding box, if it's a right rectangular prism, one of the nice things about it is that when you go to do a collision with a ray, right, because that's what we're trying to do here, when you're doing collision with a ray, you actually can just take the min and max of these things to figure out where the ray is probably going to hit you. It's actually not that hard, right? Because you can figure out what the closest point is going to be on here. You can figure out whether you're inside or outside of it, right? So you can usually do some pretty good stuff in terms of figuring out where you're going to intersect one of these things if it's a ray. For example, we can immediately discount all of the back faces, right? Just by classifying which side which direction the ray is pointing, right? So if the ray if it's an axis line bounding, it's so simple to figure that out, because the sign of these values relative to the center of this thing is going to tell us which side it's on, right? If it's got a negative x relative to where we are, then we know that this face is not going to hit. It's got to be the negative x facing face that we would check. And so we can immediately, just using like the sign of the elements after a simple subtract, we could do a lot of nice stuff. We don't even have to do dot products to figure out which of the faces is in the mix. We can literally just use the sign of the values to see which faces we're even testing against. And then testing against the faces is even simpler, because the faces themselves only really have one parameter in the mix, right? Because you know that they're always going to be aligned to one of the primary axes. So again, that simplifies that intersection equation down as well. And changes it to just a simple like range comparison. Once you do the one divide to figure out where you would end up on the face, and then you can do the range comparison. So we have a lot of options of simplifying down how we test these things. And so I think that might be a good operation as well, because since we know that so many of our things do look that way, just looking at the world. Let me go ahead and turn the lighting off here so we can just inspect it a little bit. But looking at the world here, assuming that, again, we change all of these trees to computing their lighting based on a cube, which is what we said we wanted to do anyway, everything here is just going to slot nicely into that concept, right? So I think that's pretty reasonable, and I think that is what I'd like to go with. So let's go ahead and just modify today. Our goal will be to modify the lighting to be working on AABBs, and then the next thing that we'll do is take that AABB lighting, and the next time we do Handmade Hero sessions, we will try to build trees based on that that sort of work in a multi-resolution fashion. And then finally, our final step of algorithmic optimization would be to make those trees, make the lighting work using those trees. Okay, if we assume that that's how we're going to do things, then when we go ahead, the first thing we're going to have to do here is when we actually push cubes on, we're going to have to push lighting cubes on as a specific thing. So lighting cubes are going to have to actually be specified directly. And I'm fine with taking that step now. So again, I want to take baby steps. This is a complicated system. I don't want to change too many things at once, just little tiny steps. Pick the simplest thing we can do and work towards the change we want to make, so that we don't rip everything apart and end up with a huge debugging nightmare on our hands, right? So if we take a look at what we're actually communicating to the render side of things, in here we've got sort of our lighting surface, lighting point, textured vertex stuff, right? So what we want to do here is say, all right, when we send down lighting things, instead of sending down lighting surfaces, right, which are currently the thing that we're talking about, lighting points will still be what we're talking about, certainly, but instead of lighting surfaces now, what we're going to talk about is something different. We're going to be talking about lighting boxes, basically, right? So instead of lighting surface, we're going to call this a lighting box. It's going to have a position, but it's not going to have a normal. In fact, it's not even going to really have a position. It's probably going to have more of a min-max, right? So we've got a minimum corner of the lighting box, maximum corner of it, and it's just axis aligned. So it doesn't get an x-axis or a y-axis or any of that stuff. That's gone. It's just min and max, and that's all. It doesn't have a width and height in that way because the min and max will completely specify it. And as far as transparency is concerned, I don't know whether we want to preserve that or not. That's going to be kind of a whole nother question about whether light can pass through these things or not pass through these things. I think we maybe want to keep that in there just nominally as a thing we might want to do, because if we put in a little mist lighting thing, I don't know. You know, we may want to play with this in the future. For right now, we can kind of ignore it as we have been. And just leave it in there as sort of a nominal thing. So now we have these lighting boxes. We don't have lighting surfaces yet, and so we have to kind of... Oh, I forgot to change that name there. We don't have lighting surfaces anymore. We just have lighting boxes. So now what we should get is compiler errors everywhere that people were dealing with these things as a single surface. And our job is to go through these and basically change them to work as boxes. Now we know that our lighting surface count has to be a lot less than our point count, but we're not going to deal with that quite yet, because again, we're going to make another step later where we talk about those things directly. And so here we go. When we look at our quads here, one of the problems that we're going to have is when we do extract reflectors from quads, that's not really sufficient anymore, because the quads won't tell us the information we need about these things specifically. So we're going to have to change over finally to actually pushing these things down for reals in the renderer, because we've kind of been avoiding that step every step of the way. And one thing we could do first is actually, I suppose we could change it. In fact, maybe this is even smaller step. Maybe I say, all right, look, let's leave these as they were temporarily. Right? And say, well, what we want to do is move to this soon. But let's leave the lighting surfaces as a thing for now. And what we'll do is change it so that we're actually pushing these things on. So instead of this sort of janky routine here that we were using to sort of port our old stuff into a thing that has lighting, let's actually go and do the actual lighting push, right? And so what that would be here is on the, I ended up in the wrong file. On the actual platform stuff that gets passed to the renderer, we're now going to really pass down lights as a thing, right? And so the way we're going to do that is we're going to pass down, when we're pushing things on, we're going to pass down, I guess, a U32 that would tell us here what our surface count is, and we're going to pass down a array of surfaces here, and those are just going to stack up just like they did before. So if we search for where we do that quad bitmap push, right, you can kind of see right here where we initialize our default render setup. We need to provide memory to store these lighting surfaces, right? So we need to put a thing in here that says the surfaces, what did I actually call this? Oh, hey, it's even right there. We need to pass down memory for that gets allocated for use by the renderer, like so. So now whenever there's a default rendered commands call, whoever is setting that up is responsible for also setting this up. What you can see is there's some Win32 allocate memory stuff going on here. Again, we can just sort of do the same thing. And here we'll just say, like, use that light data width. So you know that's the maximum we can have at the moment. And later, again, we'll probably change this stuff to be a little... Once we finish this up, we'll probably save it to something reasonable. And you can notice it's marked as non-restored because if you use the like playback and recordings features, we don't care about this. It's transient. So that's about it, and that will give us what we need, right? Yeah. Hold on one second here. I want to make sure I'm calling this correctly. Yeah. All right. So now those lighting surfaces can get passed, can be sort of pushed on directly, and we don't have any lighting points yet. So I think probably while we're at it, we want to push the lighting points on directly too. So if you come down and look at what we were doing, right, we were computing these lighting points by just arbitrarily pushing them on here. I think while we're at it, we want to move both things over because we wanted both things to be pushed there. So I think we also want to say light points equals light points, like so. So we kind of want to say, all right, we've got lighting points. Oops, having a lot of spurious caps lock pushing problems. So something like this. And then again, the Win32 stuff will have to do the same thing. I don't know why we're quite doing it this way. I don't know why we don't just say arrow base after it. I couldn't really tell you. Because we don't actually use these anywhere, do we? Oops. Yeah, we don't. So you don't really need to do this. You can just do this. Oops. Right. So I don't really know why I was doing it before that way, but I don't know, I was. So maybe the better way to indent that is like this, so it can be a little more legible. But that's it. And so here, if I want to do lighting points, again, the same thing. And also, this should just be whole lighting surfaces and whole lighting points. So that's the correct size of the things. And we're going to do that many of them for now. That memory gets allocated and then passed down. And then you can just sort of fill it up. So this gets us out of the problem where we were having to store these separately and generate them every frame or whatever, where now they'll just get pushed directly out the renderer. So this will get generated every frame, but they'll get generated directly where they were supposed to get generated instead of the sort of port thing that we were doing before. All right. So in order to update this to this new routine, to work the way the old routine was working, what we want to do is basically get rid of the extract reflectors from quads function, more or less. We want to pretty much eliminate it, right? So what we want to do there is we want to say, okay, let's start eliminating the things that does slowly but surely. In order to do that, what we want to do is go into the renderer, and when it's pushing lighting on, oops, which it knows that it is because, we've got sort of our lighting enabled stuff happening here, as you can see. Hey, there, we're entering a second hour. So we have another hour to go, which is nice. Thank you, Insobot, for basically telling us the exact right thing. So anyway, when we go ahead and do a push cube or things like that, if the lighting is enabled, we know that we're going to push on lighting information as well. And so in order to do that, what I want to do here is actually push things on coherently that make sense. And we don't really have this lighting structure worked out exactly the way we want it probably yet, but it's pretty close, right? The thing that's a little bit weird about it is the cross-indexing, which is a little weird. So you can see you've got like a lighting surface here, and then you've got a lighting point, and the lighting point kind of talks back to about which its lighting surface is. And so I don't really know how those really want to... I don't really know exactly how we want to treat those. Because it would be nice if everything just corresponded directly. The problem is that in order to correspond them directly, we couldn't more highly sample some surfaces than others. And we also have a problem of sharing light points between surfaces. And I'm not sure exactly how we're going to do that, but we're going to want to do that. And so I think what we're going to have to do, at least my guess is that this is going to have to be a general index back to any lighting surface, potentially, and potentially two lighting surfaces. I don't know. It's going to be a problem. Let me just put it to you that way. We're going to have to do something with lighting points and surfaces that allow them to be corresponded in a flexible way. It may require essentially a linking table kind of approach where we put pairs of indices, lighting point, surface, and you can have any number of those pairs that you want. We may have to do something crazy there. Right now we don't have to because we're not doing the thing where we put points on the borders that share behavior between the two or anything like that. But we may get to the point where we're doing things that are somewhat complicated there. So there's a couple different ways we can do it, and I'm not sure exactly how we're going to. But one way that we could do it in the future, and in fact now I'm saying it's probably a good idea, is just to link light points together. So if we have 2 points that want to become the same, what we'll do is we'll have a separate pass that happens afterwards that just averages those together. So something like that where we're basically saying, and just to, I'm sorry to be throwing so many things at you here. I realize it's a lot to take in, but lighting is complicated. It's one of the hardest things you can possibly do in graphics, full stop. So what I'm saying is we talked before about how I will eventually want to get rid of this scene here, and there's pretty easy ways to do it. What I was talking about is you want to share lighting information across that boundary. In order to do that, right, we need points that will say, oh, interpolate, the lighting along here is the same on either side of it. So we need to put interpolation points there that know that the lighting should be equivalent. But remember, we want these lighting points to be associated with surfaces so that when we hit surfaces, we know to distribute light to the points. We can't have lighting points that are shared between surfaces without more complicated linking. But what we can do instead is just say, all right, let's just put points duplicated that are just close to each other, and we'll just say after you're completely done, average those two together and update the light with that information, right? So there's like a post pass, like a convolution on the lighting that happens to smooth it out along boundaries that should not have seams. And so that's, I think, probably where I'd go with that. Sometimes you want to duplicate effort to avoid complicated linkage. And I think this is going to be one of those situations, right? So that convolution process, I think, would give us a lot of nice opportunity to smooth out the lighting in places where we know we're never going to sample it high enough to not have at least a subtle seam in it, right? So that's, I think, where we're going to go with that. As I'm saying it out loud, I'm really liking the sound of it, so I think that's probably where I would go with that. So let's come in here and now let's work on getting these lighting surfaces pushed properly here. So what I want to do is I want to push these on in the same way that we're pushing on the existing ones. We've got basically all the information that we need to do so because we're going to push on the cubes, the quadrilaterals on the faces of a cube, so we know we can first push the lighting surfaces that are exactly those, right? So what I can do here is sort of say like, okay, I've got a lighting surface. And in fact, maybe I'll just call it surface here. And that's going to be equal to something. We'll figure out where that goes in a second. And then what I'm going to say is like, okay, surface 0, or rather just surface, blah, 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 surface, blah, 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 right? And then I will plus surface. And I'll just do this for the 6 faces that I want to have there, and then I'll be done. So what I'll do is say, all right, the point here, I have to figure out what that point is. We already did the work of figuring out what that surface point is in the other one, but we can probably do something simpler here because with this cube, we're getting exactly the information we need, right? So you can see here we're getting all of this information. We know what the normals are. We've already said what they are in a lot of cases. We know what the points are, blah, you know, et cetera, et cetera. So we kind of know all the information that we need here. We don't even really need to do arithmetic on these probably to get back the information we want, like we were having to construct them before, because we actually know the real cube now. We can just push the surfaces on directly, right? So we know we need a P and an N. The surface, the transparency, I don't know how we were doing that before, but I'm going to set that to 0 for now because we don't care what it is. We need the width and the height of that surface. We need the x-axis and the y. And you can see how much information is getting pushed on here. It's way too much, which is why switching to AABB is going to be great here. We're going to simplify all this stuff and just really get it down to a much more straightforward thing we can use for lighting transfer. That's going to be really nice, I think, in and of itself. That will actually speed us up probably, maybe not 8x, but something like an 8x speed increase, probably just from stopping proliferating cubes into their faces for no reason, right? All right. So if we take a look at the surface points here, what we want to do is say, okay, when we created these, we said, all right, the nx, px, ny, py, nz, pz, that's the negative maximum x, positive maximum x, negative maximum y, positive maximum y, and so on, right? So this cube is always axis aligned in this case already, so we don't really even have to think about it harder than that. And we already have the min-maxes that we need here. So what we can do is just start talking about the center point, but the center point we have, it's just p.x, p.y, p.z, whatever. So when we're trying to produce, say, one of these surfaces, all we're really saying is, oh, let's take like the negative x, negative y, negative z. That would be the corner, the most negative corner point, right? I'm sorry, this is probably something where you would like a diagram to understand it better. So we have a cube, it's axis aligned. Here are the axes of the cube, x, y, z, right? All at right angles. And if you think about what we're talking about here, negative x, negative y, negative z, it's this corner down here, right? What we might want to do is say, well, let's produce this point, right? So all we have to do is say, well, that point is going to be the center point of the cube with just its y value changed to negative, right? So if we were instead to say, start at the center point and just take the negative y, right? It's hard to type with a pen in your hand. Or the negative x, or the positive x. That gives us the center points of each of the faces, right? So we can trivially arrive at all 6 of these just by taking the positive and negative faces. That's all we need to do. Oops. And again, you can see how many things we're pushing on for a cube. It's just a ton of work. So we'll get to see all of this collapse to a much simpler thing when we switch to the AABBs. So that's going to be very satisfying, I think. All right, so as we push these surfaces on here, we have to pick one of these to do. So I'm just going to do like negative x first, then positive x, negative y first, then positive y, negative z first, then positive z. And now we have each of the center points of all of our faces. Now, the other thing that we know is generating the normal is actually extremely easy because the normal is always going to look like an axis-aligned normal, right? So we just have to know which one of these we're doing. Well, if we flip back to the diagram, what you can see is that whatever the thing is, so here was the y-axis, I replaced the y-coordinate of the center with the negative y. Well, then the normal is just a long y negative. So whichever one I put in there is the one I do. If I put negative x in there, right? If I put positive x in there, if I put negative y in there, if I put positive y in there, negative z, positive z. So hopefully that's all very clear. Like hopefully you can see all of the things that are going on in that geometrically are very simple and very straightforward, and it just allows us to generate it without doing any arithmetic like we were doing before. It's just rote. It's like a tableau. You can just read it directly off. Now the width and height are a little bit more finicky. Again, we can read them directly off, but we have to make sure we're reading the right thing off. Now, fortunately for us, we actually only have two values, radius and height, so that makes things a little bit easier. But we're going to have to adjust the z values here, because we did a little bit of a weird thing when we were specifying these cubes, where we specify the top point. I don't know why we decided to do it this way, because I think because we were thinking ground-based. I really kind of wish we didn't do this. I don't know that I want to change it right now, but I kind of want to change it right now. Like I think this is... It's whatever. It is what it is. So we're going to have to go modify those z's later, but I'm just going to do everything uniform, and then we're just going to touch up the z when we're done with it, right? Because actually the negative z, you can see, it's still, I think it's correct what we wrote, but you can see that these two values are a little bit different. So, you know, you have to think about them a little bit differently when we get to them, that's all. So width and height are going to be a little bit more finicky. X-axis, y-axis are going to be not so finicky, right? So let's just go ahead and look at those first. So when we're talking about positive x, which is going in this direction here, so for positive x, we know that our x-axis, right, is this way and our y-axis is this way. So we know that for positive x, the x-axis is actually the y-axis and the y-axis is actually the z-axis, right? Does that make sense? Oops. Right? So z-axis is going along our y, and our x-axis is going. I'm sorry, x-axis is going along our y. Our y-axis is going along our z, right? World z. So that's going in there. On the other hand, in the back version here, the back version of this cube where we were talking about negative x, right? Oop, and you know what? I just put that in the wrong place. Go. So when we're talking about the negative x-axis, the y-axis is still going to be z, right? It's still going to be facing up. But this time, instead of pointing this way, it's going to be pointing this way, right? So it's actually going to be negative y-axis for our x. And that's just because we're on the back face of the cube, right? So we've rotated around, and we want to still keep the winding uniform, right? So there we go. All right. Now let's talk about the y ones. So on negative y, you can see again, z is still our y-axis, and our x-axis is actually our x-axis, right? So on the negative y front, we have an x-axis that is the x-axis, and we have a y-axis that is the z-axis. When we go the positive route, we're rotating around here. Our z is the same. I mean, our y-axis is still the z-axis. Our x-axis is going back the other direction. Right? And then finally, when we get down to our z's, for our z negative, right, you have to imagine looking at the cube from the back. Or, well, I mean, I guess we're going to do it the other way around. If we start with our positive z-axis, right, and we're looking down at this, there's our, would be one way of doing it. It doesn't really matter which way. We can always pick, as long as these axes are stable, it's fine. So if we take a look at how we're doing this here, negative x-axis is going that way. Positive y-axis is going this way. So negative axis is our y. Negative x-axis is our y. Positive z-axis is our x. And if you imagine that rotating around, again, this axis doesn't change, so the positive y-axis is still the x, right? As we rotate this around, you can imagine the x-axis is still going on positive y. But this is different now. So instead of the x-axis being positive, sorry, in negative this case, it becomes positive. So there you go. Now we filled out all of the things that we're pushing on there. Finally, we have to do the rest of this stuff. So what you can see here is our light count in this case is always 4. Our light indices in this case, you can kind of see we started with it here, is just going to be light index. And we'll just update that as we go. And that will just become like so. Now, one of the problems with that is this, again, has to kind of be placed down in here correctly. We can worry about that in a second. I suppose what we really want to do here is maybe have these surfaces still be coherent, but we'll deal with that again in 1 second. Let's just finish the width height stuff instead. All right. So we got to look at the width and height here of these things. So we're now talking about the negative x direction, right? So the negative x direction is the thing that points out this way. And so what we said is that our negative axis is negative x-axis negative y-axis is our x, right? And so that was what we were talking about. We were talking about what did I say? Negative y-axis. Yeah, negative y-axis is our x-axis, and z is our y-axis, right? So width and height have to be measured along these. So our width is going to be our y width, right? And we've said that that's the radius of this thing, right? Since it's the width, we need to multiply it by 2, I believe, because radius is, goes in both directions. And so really all we have to look at is what are the two we're doing here. And so for z, we are using height instead, which is a total. So height is actually just height in this case. Now the same thing is going to be true here since we're not changing that interpretation at all. It's going to be the same in both cases, right? We then have our ones for negative and positive y. So negative and positive y are going these ways. So again, our x is our radius, but our y in this case is going to be a height-based thing. So I think we've still got the exact same concept going on here. But our z, on the other hand, takes that out of the equation. So for our z, it's always going to be radius, no matter which side it's on. So it's always 2.0f times radius in this case. And then what we need to do is we need to make sure that these surfaces that we've pushed on correspond to the light points that we push on as well, right? We need to push on individual points that are kind of on these things. And so if we go back and look at the, I wonder if I kind of was just wasting everyone's time there by doing that too, because the other thing I was thinking is, can't we just copy the routine that we were doing over here? Like, could we just copy this thing? Shouldn't I have just put this thing directly in there? In fact, why did I just waste everyone's time by doing that? Well, I don't know why I wasted your time doing that. I'll be honest. Don't have a lot of explanation for it. But what I will do is I won't waste your time any further. What I will do is I'll say, all right, let's grab this chunky monkey out of here and put that in. So once we have the surfaces, we can generate the points, right? So once we have the surfaces, we'll generate the points from the surfaces just by using the subcounts here. So we'll go through here and generate them this way. we'll iterate over the lighting points that we're going to push in here. And we have to reset our lighting index variable for that. So when we go through here, right, we're going to want to reset this back. Then we're going to want to push these on. We're going to push these on exactly the same way as we were before. And so we need to now have, for our lighting points, we need to have some sort of an idea of what's going on here. Inside the platform layer, when we push these lighting points on, we do P, ref C, N, and surface index. So we need, you know, these guys here. We don't initialize these because these are not part of it yet, so we'll let those get handled a little bit further down. Although, I guess ostensibly we should move this into here eventually in some way. I mean, in fact, I could just do that in this pass as well. Yeah, I guess I could just do that in this pass as well. All right, well, that's fine. Let's go whole hog. So in the lighting solution, some world mode here. We've got sort of the informational stuff we were doing before, where we've got emit C0 and emit C1 and average direction to light. Those things get initialized in certain ways. The average direction to light and C1 are used in the computations and held. Although average direction to light gets reset here, which is wrong. So we had a bug in here that we didn't address. Average direction to light is supposed to be held over, correct? Yeah, that was a bug. We were probably getting better lighting results than we thought we were getting because we had a bug here. I say. Hold on 1 second. I want to test something. So this is what we were running before. And you know what? Let me generate a small world so we can run the lighting in interactive time as well. So here is the old version. And here, let's see, these are cleared normally, right? I think. So let's just see what happens if we don't clear that value. Because I thought, weren't we lerping those? So how was that working? Let's maybe I'm wrong. I must be wrong. Because I thought we were blending those values over time, but what are we blending them with? Okay, so we do have never mind. I was a little nervous there that we were clearing the wrong thing. So that's okay because we do have it stored in a separate one, so it's all fine. Yeah, and we just lerp between those two, so that's fine. Okay, okay. I got very nervous there for a second, but we're all good. I was like, it should have been super flickery and weird, like, and wrong. Not flickery, but it should have been really wrong and dark if we were doing that. So I was, like, really confused. I wanted to make sure I wasn't totally crazy, but I'm not. So anyway, going back here. So if I jump back to the render group where we're pushing these lights on, here we go. So if I push all these surfaces on, and then I want to push these points on, average direction to light is just a temporary rendering buffer. So it doesn't need to get cleared here because it can get cleared anywhere, right? It can get cleared back in the other routine or whatever. So that one's not a big deal, but the emission is actually an important part of the light information, which needs to get sent down on the frame because it's the new emission that's being said, you know, this is the emission that we're actually sending down. So we do want that to be stored in the render information as well. And so I'm just going to put that, at least temporarily, into the stuff that we passed down. I'm going to bake that into the lighting point. And the reason I'm going to bake that into the lighting point is because I think we're going to use buffers for iterating over these. And so I think there'll be a source buffer from the lighting points. We'll do a pass first that, well, I don't know. Since I don't know, I'll just leave it separate. I'm getting ahead of myself here. So emit C0 will go here with lighting points, and it'll have as many in it as this does. And so what we'll do here is, again, say that whatever the emit C0 is for this particular light index is going to be the max emission times whatever the emission is for this value, which should be just a value right here. We don't have to get it out of a vertex or anything because we can just use it directly. So we'll put the emission in there, and then we'll continue on, right? All right. So we're getting closer, but we still have a few things to deal with here. So we have to figure out which order we need to push the surface in to line up with these, right? So P0, P1, P2, P3 is P0, P1, P2, P3 is NNP, PNP, PPP, and PP, right? So this is a positive Z face of the cube, right? So the first thing we're pushing is the positive Z face, and this is our positive Z face. So this goes first, right? The next thing we're pushing is 7654. 7654. That's the negative Z face. So positive Z face, negative Z face. What are we doing next? 4510. 4510. That's the negative Y face. This one right here. Should keep track of where I am. So we push positive Z face, negative Z face, negative Y face. I'm just going to guess positive Y face. Let's see if I'm right. 2673. 2, 6, 7, 3. Yep. So probably negative X face now. And then positive X face. Let's take a look. 1562. 1562. Lovely. So here we've pushed on the surfaces now in the same order that they're getting pushed on in here, which is obviously important. And so then we need to make sure that our light index lines up. This is really cheesy. I'm only just not caring about this because we're going to delete it like immediately after we get it working. So we're resetting it. We're pushing on the points. Resetting it again, pushing on the points, right? But that's really all we should have to do. So now what we need to do is actually grab these out of somewhere. Now we've got our rendered entry texture quad stuff here where we got entry, right? And this is using sort of this information for where we're supposed to push the quads. We need to specify, we need to be able to get out the rest of the stuff from the render group as well. So like this, we need to access these two things, right? We need commands surfaces and commands points. So in here where we do lighting surface, surface equals command surfaces, command surface count plus equals 6. What we need to do here is basically say like, okay, commands surface count. We need to make sure all these indices line up, and there's way too many of them, right? So we need to be able to say like, okay, what's the surface index here? The surface index is whatever the surface count was. So now we've got the surface index properly here, and then all of these can, all of the points can know what their surface index should have been, I guess is what I'm saying there, when they get pushed on. We'll deal with that in a second. So anyway, here's our surface indices. We know which surface index we're on. We go sort of through them. We'll use this in a minute because we don't actually need it for anything at the exact moment. We update the surface count. So this should push all the surfaces on. We just need to know what this commands value is. And I think we can do it just by doing group commands. I think it's literally just that, right? We also want to assert that surface index is, I should say, commands.surface count is less than or equal to light data width, like so. And this should push all of those surfaces directly on. We then, when we're pushing the points on, need to do exactly the same thing. So we have the light index stuff here needs to be on here. So this is actually just group commands light points. And similarly, we have here when we're doing this check, this is going to be group commands light point count, like so. All right. Don't ask me what that's supposed to be. All right. And now we need to allocate these points per surface, right? So really what we want to do is loop over the surfaces here, like so. This would be surface width and height. We need to know the surface index as well, which should be pretty straightforward. And I think that's all. I think that's all that we actually use. All right. So yeah, in here we can just say, all right, we know that our surface index, this is our starting surface index right here. Right. So we know that our surface index we're just going to loop over all 6 faces. Once we get the surface index, we can pull the surface out from that. That's actually fine, but all right. And so for each of these points, the point P is going to have to be something on the surface, right? So what we can do here is say, well, you know, we know what the point, we want to change this from being generated off of vertices, which is how it was working before, into something that's generated off of the center point, probably, right? So what we can do here is say, like, okay, the vert well, I can really even just translate this exactly. So if we just use the surface's x-axis that we've already computed and the surface's y-axis that we've already computed, we can replicate this in its entirety by just saying, all right, the vert, we know what this would be. It's just going to be kind of annoying when we write it out. But if we just take the surface's p-value, then we just need to step backwards by the x and y axes by half the width and height of the actual thing, right? So we just need to say, like, half, we're going to step backwards by half surface width, backwards by half surface height. And again, that's totally unnecessary because we could just bake that directly into here because we know the sub width is just half of it already. So I guess one thing we could say is just like, all right, forget that. We know we're subtracting off the 0.5 here, so just get rid of the 0.5 of this or whatever, but let's just replicate it exactly for now. Right. And again, this is x-axis. Emit C0 in this case is just our group commands, emit C0. Max emission is sort of the value we haven't really decided what that value actually is ever going to be, so that'll be something that we work on a little bit later, but it's just a way of encoding our light sources. We'll handle that like so. Yeah. Cannot convert F32. Ah. Yeah. And there we go. So now we have ostensibly started pushing these things on to that memory. Oh, and we need to allocate this in our Win32 layer. So in here, and these will probably be transfer buffers eventually, because this is all stuff that goes to the card. So I'm not sure how this will actually pan out when we finish up, but you know, it's going to be something like this. And then when we do our default render commands, you have to pass these in. Like so. So now that stuff should be getting pushed on there. It, however, is not actually going to get used. And we have to... that's odd. Is this not getting reset? Oh, right. We don't reset this. So we have to... where is our, there we go. So we have to clear this out every time we restart as well, right? So we have to clear out our surface count, we have to clear out our light point count, and we have to clear out our emit, well, our emitters just use the same indices, so that doesn't actually need to get cleared out. So at least in theory now, we should be good to go on the lighting front there. All that stuff's getting pushed down. We're just not using it yet, right? So now we have to see about actually using it, and we have to see about pushing the light points on. Are they all getting pushed on correctly? I think they are actually getting pushed on correctly. So now, or at least we made an attempt to push them on correctly. We may not have done it correctly yet. So now we just need to go and actually start using them. So what we want to do here is when we do our extraction process here, we do extract reflectors from quads. What we want to do is say, well, we don't really need to do that anymore. Let's just obviate the need for that entirely. Get rid of all this, and the only thing we really have to do then is let's clear out like emit C0. I mean average direction to light, right? Because that needs to get cleared properly. So average direction to light needs to be zeroed. I don't know if we have a thing to zero here. Zero size. So if I want to, I can zero out that entire array. And so now that's cleared. And now we don't do the extraction process at all. We just need to hoist these values out here and use them, right? So what we want to do is in the lighting solution, where we've got like the surface count surfaces, the point count points, the emit C0, emit C1, direction to light, last is valid, blah, blah, blah. What we want to do here is we want to start taking some of these out. Okay, and so now what we want to do is we want to get those from somewhere else, and you know, that somewhere else is going to be the lighting commands. So we have to, when we go to do that extraction, what we need to do is actually extract those from exactly that place. Now, I guess we could actually do this in a really smoothly kind of way by just saying like, all right, well, you know what? Maybe we just actually copy everything for the moment, you know? So let's just do this. Solution emit C0 is going to come from group commands emit C0. Let's just copy all this stuff. Surfaces, light points, and emit C0. Surfaces, points, emit C0. And then let's also just copy the point counts. So now we're just going to bulk copy that stuff in here, and now we can actually debug this as we go. Oops, and this was already a local, so I could just do that. So now we do the extraction, we're literally just copying this stuff out into our own temporary space, working on it, and then putting it back. As you can see, when I'm doing this, we actually seem to have gotten correct results, which is kind of surprising, to be honest. But it seems to still be behaving the way that it was behaving before. It does seem slower now, which I'm not sure exactly why that would be, but we can investigate that a little bit further. I just wanted to make sure that it was working at all, and it sort of is. One of the reasons it might be slower is because of all this copying that we're doing for no reason. That obviously could be a big part of it. We are compiling in optimization mode, but that copy could be kind of slow. So let's go ahead and get rid of the copy and get rid of the extraction altogether. We can now get rid of this because we don't need it anymore. I will go ahead and nuke that. There we go. And then when we do extract reflectors from quads, where we were calling that before, I'm just going to put this directly inline here. And I'm going to eliminate these copies by just making them be local pointers, right? So where we do extract reflectors, quads can go. What we need to do here is just say that solution surfaces equals group command surfaces, solution points equals group command light points, and solution emit C0 equals group commands emit C0, like so. And we need to move this stuff down here. This needs to happen at the end, like so. So when we do this right, now we're going to grab all the pointers out. We're going to do our, we're going to save our average direction copy here, and then we're going to clear it. That's really it. Not a lot more to it than that. So I think we're all good. The only question is, hey, when we're storing these here, we should probably now do this a little bit more sane. We should probably say something like, well, for the points that we're actually using, so, you know, this is probably more appropriate. Let's not clear parts of the buffer that we don't actually use, or save parts of the buffer that we don't actually use in that case, right? But that's about it. So assuming that we're going to do everything that way, then what we want to do is, and we have to do some stuff here to make sure that things, as we add more points, won't be completely borked there, but that's sort of a separate issue. We have to zero some things out and stuff like that, but we'll get to that a little bit further down. They will already be zeroed because they're Win32 initialized blocks, so that part is easy as well. But anyway, what we need to do now is make sure that we're not using array count anywhere, because these things are no longer directly accessible. So this, you know, becomes that, this becomes that, this becomes that. So you have to watch out, right? So I'm just going to go see if we have any other size ofs in here that were happening. There isn't. And I'm going to see if we have any array counts in here. It doesn't look like we do. So I'm going to see if that works a little bit better. Or I should say if it works at all. Because I don't actually know. It does appear to be working. I'm going to take a look at the profile. You can see update and render world is taking all the time. That's the compute lighting stuff. I'm going to go ahead and take a look at the. I'm gonna add some timed blocks in here. Is that all I have to do? Yeah. Assuming that all the time will be spent in there, but I don't actually know. So compute light propagation is taking all the time, which is what I had assumed would be happening and is happening, so that's good. The only problem is I don't know why it seems significantly slower than it was before, because I think it was running faster than this before. I could be wrong about that, so maybe there's no need for concern, but I was trying to figure out whether we were pushing too many points on potentially. So it might be nice to see what the point count is, for example, in here. In the renderer, how many lighting points it's actually doing, how many lighting points it's actually using, or stuff like that. So I might just add a thing that allows that to be output. I know in our debug system we have the ability to say debug value. I just never remember how it works. So it looks like you just say debug value. That seems pretty simple. So yeah, if I was to do that here, would that just work? I don't really know. I guess it does. So we've got 1,849 points and 462 surfaces. So that does still seem like the right number. So yeah, I'm just not sure if we accidentally slowed things down, because I don't remember how fast this thing was running before. I think maybe it didn't slow down. I don't know. We should probably check. We're going to have to optimize this all anyway, so I guess I don't really care too much, but I probably should have double checked that we didn't slow it down. It would have been nice. We can go check the video, I suppose. All right, so that's how we're pushing all that stuff on there. And now the question is just, and you know, I might have pushed, I don't know if I actually pushed everything on exactly right. Fortunately, it looks like I did. I mean, all the faces seem to be responding properly. If I switch temporarily to what it looks like, what the incoming light is, you can see that it looks about right. There's yellow incoming light to all those. There's white incoming light over where the white light is. It all looks pretty reasonable, right? I can switch the number of iterations down very low, and then we're back up to 60 frames a second. There's one iteration. There's two iterations, and so on. You know, and another thing that's worth noting is, since we're sort of doing smoothing over time now, we could allow light to propagate, to continue propagation across frames potentially. I don't know how I feel about that necessarily, but you know, it's worth noting that one of the things we could do is say, well, lighting bounces can happen outside of a frame. So, you know, you bounce light somewhere and it can bounce light again next frame that it received the previous frame. I don't know if we really want to go that route, because I'm not sure how, you know, you have to decay those over time in order to make sure that they would not bounce around forever or whatever, but, you know, we'll see. Anyway, so given the fact that that's all fairly reasonable, now the next step that we would do is change these to AABBs so that we just pass down AABBs directly instead of having to pass down all of this extra mumbo jumbo, right? I don't want to do that yet because we are out of time now. So what I want to do is next time, that's the next step we'll take, change to AABBs so that everything just works on AABBs instead. And off we go, right? So I'll go ahead and go to the Q&A for now. And hopefully YouTube stayed up the whole time. All right. How come Bink 2 isn't used prevalently at that in video playback across all of the video playbacking use cases? Why is it the incumbent sovereign only in video games? Well, I think two reasons. One is that the companies that get together to do the standard like MPEG license are all kind of in a cabal together. They all do like this giant patent nonsense and make this like, you know, codec that they're all going to put in their things. So like, you know, that's why like Blu-ray or something is this standard. It's because all the people who make Blu-ray players and Blu-ray discs all get together and have a giant festival where they make a really crappy standard and then ship it, right? But the other reason is because Bink 2 is very specifically designed for games, and it very explicitly doesn't do things you might want to do if you weren't worried about games. For example, encoding is very slow in Bink 2 because it assumes that what you want to do is bake all of the videos for your games down, and you want to put a lot of thought into the encoding of those, and then you want the playback to be extremely fast. But that's not true of other things. Like, for example, this is a live stream right now. I don't know that Bink could live stream something. Its compressor is not meant to run in real time, right? You know, maybe it can by now. I don't know what they've done to it since last I worked on it, but so it makes very different trade-offs than you would for a general purpose codec that doesn't have any specific use case in mind, like MPEG or something like that. And the other reason is because Bink will sacrifice compression quality for playback speed, for example, right? So one of the things that Bink 2 definitely does is it makes sure it uses very little memory and it makes sure it uses very little CPU, right? As much as possible. That's not, again, true of MPEG. MPEG is maybe just going for the like best quality with the highest compression, right? And it doesn't care if it's using your entire machine resources just to play back a single video. Bink wouldn't want to make that decision because Bink knows that you want to be doing loading and processing of your assets while you're streaming a video so that there's not a load screen or something, right? So that's probably most of the reason. Bink 2 just isn't trying to target general purpose. It's only trying to target what game people do. That's what it tries to do. That's who they sell to. And that's intentional to a large extent. All right, so light leaking. It's entirely possible that we have light leaking because when we push these things on, we may have pushed them on incorrectly, right? Let's take a look. Could you be more specific about where the light is leaking? I guess maybe the yellow light is leaking. Is it leaking? I can't tell. I'm not seeing the leaking. I don't see any light leaking at the moment. trying to see if anyone has some, can say where the leaking is. I thought I saw the light leak through the bottom wall. That would be the red wall, right? Well, remember, we can push ourselves through, right? So what you may have seen is this. If we allow the cube to penetrate through this surface, which is the only one blocking it, then it will leak through, right? So right now you can see we're not getting any white light leaking here, but if I push through, then you would get it. That's not a leak. That's because we assume you don't interpenetrate, because you normally wouldn't be able to. Asaf said that I'm getting pretty frequent audio popping. Other people noticed it as well. I recorded a sample here. So I'm assuming that's the YouTube streaming from OBS not working, or maybe YouTube isn't working. Because I'm assuming that the audio popping is not going to be on the recorded version. Unfortunately, I'm not sure how we would fix that. Maybe I have to change the encoding settings for YouTube or something. Not sure. When you write code in exploratory fashion and you end up with something that works well but is too large and complex to fit in your head at once, how do you simplify it back into something manageable? Well, the same way that you do anything else, right? Like you go back through it and you look at what it's doing and you say, all right, how can I break this into chunks that I can sort of carve off as something that it does, right? So like with the light, we're like, oh, okay, you know, maybe it does this particular pass and then it does this other particular pass. Let's break those into two functions and sort of document what they do and then lock it down. Like, okay, here's what it does, right? So usually what you do is you just take sort of spaghetti-ish stuff, right? Which the light system is kind of now. It's like pushing it all over the place, right? And then when we know that it's kind of working the way we want, then we just go in and we start isolating the parts and how they work, and we just lock those down, right? Make them nice and clean and say, here's how the data comes in, here's how the data goes out. Everyone understands it now, and off we go, right? It's really not that hard to usually to go back through and just go, what is this actually doing? How do I break this into sections? That I can clearly say what they do and what they don't do, and what they ingest and what they output, right? Will you continue dual streaming to YouTube? I'm not going to dual stream. Like, I'm only going to stream to one place. If we can get the YouTube streaming working well, we could just switch to that permanently. I'd be fine with that. But it's very hard to get dual streaming to work. It's not reliable, and OBS doesn't support it natively. So I'm not going to go down that route. Are you concerned with compile times at all so far? I saw CTime reporting 2.7 seconds. No. That's plenty. Fine for me. That's 2.7 seconds is the optimized build. So if we switch to the debug build, it's only 1.64 seconds. So I'm fine with those two as compile times. Anything under 10 seconds, I'm usually fine with. I find anything over 10 seconds and I notice the iteration. I notice that like by the time I switch here, it's not ready to run yet. Anything under 10 seconds, I'm usually fine. No more questions? If there are no more questions, then I will end the stream for today. For today. All right. Thank you, everyone, for joining me for an episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to... Well, you know what I just realized, though? Before I do end it, I don't know if there were some questions on the YouTube one, because that would not have shown up. Did anyone have questions on the YouTube chat? I don't see any Q colons on here. All right, looks like not. All right, thank you everyone for joining for today's episode of Handmade Hero. It's a pleasure coding with you as always. If you want to follow along with the series at home, you can always pre-order the game at handmadehero.org, and it comes with all the source code so you can play around with it. We also have a schedule bot if you want to know when we're going to be live, and the little live now button will tell you as well periodically. As soon as the schedule is updated, it will tell you how long it's going to be till we're up. Obviously, once we're done, it will switch to nothing scheduled until the next schedule gets posted. We also have an episode guide. Go if you want to check out past episode of the series. A contribute button if you want to contribute to the how should I put it, community projects like the 4Coder editor we use on the stream, or although I think that went to itch.io now, so it'd just be the episode guide, the hosting for the Handmade Hero forums and the Handmade Network stuff, all that sort of thing. We do collect community contributions to pay for those projects, and we just give out the money to the folks who are doing them. That's about it for today. I do not know if I will be back next week or not, because I may be out of town and away from this computer on the days we would have normally scheduled them. I might try to reschedule them for other times. We'll see. So no process on that, but we will be back the week afterwards regardless, and then we'll be regularly scheduled broadcasting from then on out. Until then, have fun programming. I'll see everyone on the internet, and we will try to figure out what's going to go on with our streaming setup in the future as well. Since now we know that Twitch is not really reliable, we'll probably have to have something back up like this YouTube situation. So we'll play around with that a little bit and see what we can do. That's it for now. Catch everybody later, and thanks for joining.